next task is to finish classwork 5. You may find the problem set in my course materials. So far, we had it solved the following equation: 36x minus 43y equals 12. Do you remember it? Do you remember our attempts to solve it?
Yes.
Yes.
On Thursday? Okay. So, according to our theorem, such an equation has how many solutions?
Infinitely many.
Infinitely many. But is it possible that a similar solution has no a similar equation has no solutions?
Absolutely.
And what is the distinction between those that have a solution and those that have no solutions?
Divisibility by the GCD.
Of what? What must be divisible by what?
12 should be divisible by GCD of 36 and 43.
Yes, here this holds. So, in general, in order for an equation of the form ax plus by equals c, it has a solution. So there exists x, there exists y with such a property if and only if the greatest common divisor of a and b divides c. Do you agree?
Yes.
And now assume that we are interested in the following equation with three variables. One equation and three variables. After all, do you have a linear algebra course?
Yes.
Do you know anything about solving simultaneous linear equations? Not in integers, but in real numbers.
Some knowledge of it, yes.
For example, say, assume that we have something like that. Assume that now we are considering reals, say A, B, C, D, E, F. Assume that these are reals, not necessarily integers. So AX plus BY equals E, CX plus DY equals F. When does this one has a solution?
Like according to our linear algebra course.
Exactly. Mathematics is unite, so it is it is the same for our course as it is in your linear algebra course. What is the condition necessary and sufficient for this system to have a solution?
So like in a reduced row rational form of this equation, there will be something. I don't really. Maybe something can help.
Probably you should consider this matrix. Which trait must it have?
Oh,
In
so
order,
the determinant must not be 0.
yes, A multiplied by D minus B multiplied by C, a special polynomial known as determinant associated with such a matrix must be non-zero. Okay, but given it is non-zero, how many solutions? How many solutions does it have? Such a system.
0, 1, or infinitely many.
0, really? Given its determinant is non-zero.
But like it depends on E and F too, doesn't it?
No, it doesn't. Really?
So 1 or infinitely many, probably then.
Do you know anything about inverse matrices? What if you multiply both sides by the inverse matrix? Wouldn't this one be the solution?
Yeah, and inverse is unique. Okay, so only one solution.
Clearly it is unique. Clearly it is unique. Given, of course, this inverse exists. But we may have another situation. Assume that we have something like that. 2x plus, say, 3y equals e. It is, okay, let it be, I don't know, c. And here we have, say, 4x plus 6y. What about this system? When may it have a solution? What is the determinant of this matrix? Let's call it B.
0.
0. Twice 6 minus thrice 4, it is 0. So that means that its lines are, its rows are linearly dependent. You can obtain one equation by multiplying the other one by 2. Do you agree?
Yes.
So it has a solution when? If and only if. Here we have what?
Twice C.
Assume that here we have twice C. How many solutions may it have? Isn't it obvious?
What, 1? Oh, no.
Really, one.
Infinitely many.
Look, one equation, and this equation is essentially the same, for they are linearly dependent. One equation and two variables. We have infinitely many solutions, but what is the form of these solutions? You may put them the following way. You can take anything for x, and then what should you take for y? C minus twice x over 3. Do you agree?
Yes.
These solutions are vectors. And what about the set of these vectors? What is it? What is the set? X of points x, c minus 2 over 3x. C over 3 minus 2 over 3x. What is it?
What is vector space of it?
Yeah.
Oh, I'm not really
Subspace.
familiar with such thing.
What
yet.
is it? It is a line. It is a line. This equation say y equals minus 2 over 3x plus 3 over 3. It is a line. Isn't it?
Yes.
It is one-dimensional. It is one-dimensional. And here we had the same. Either no solutions or Or we had a one-dimensional space of solutions. Do you remember? X0 plus 43t, Y0 plus 36t, depending on t. Still a one-dimensional space with one parameter. Is it clear? And generally, the number of parameters, the dimension of the space of solutions is just the number of variables minus the number of equations. It is an important guiding principle for linear equations of any kind. Whether they are Diophantine equations as ours are, that is in integers, or they are your regular equations with real coefficients. But here we have how many equations? How many variables? 3 variables, x, y, z. Isn't that clear?
Clear.
Yes.
3 variables, one equation. So apparently, if there is at least one equation, we shall have a two-dimensional space of equations. I will not continue this line, but in general, the set of all possible equations will be parameterized with two integer parameters, not just t, but say s as well. But look, do we have at least one solution? This question is much easier. Is there a solution in integers? That is, in triplets of integers. Do we have a triplet of integers with such a property? In order to prove, it is enough to provide one. Any ideas? For example, can we somehow reduce it to an equation in 2 variables, for which we know everything, for which we have a complete theory? Is it that hard? Ladies and gentlemen, let us assign some value to one of these variables. Let z be what? At your choice.
0.
0. But will it work? If it is 0, then our equation is equivalent to the following. 6x plus 10y equals 29. May it have a solution?
No, definitely not.
No, because the greatest common divisor of these two is 2. It doesn't divide 29. So there is no solution. There is no solution where z equals 0. But you may, we have more tries. We can take something else than z. In principle, we should take here such a number that 29, our equation is equivalent to the following. 6x plus 10y, 6x plus 10y equals 29 minus 15z. Do you agree?
Yes.
So when does it have a solution? We see that it has a solution if and only if 2, the greatest common divisor, divides 29 minus 15z. It has, or better, we may put it the following way. It has a solution where z equals some fixed value z0, if and only if this value is even. Can we make it even?
Yeah, that 0 is what then?
No, if z equals 0, then 29 minus 15z is not even. It is odd. It is 29. But what should we take for z in order to make this number even, this one, this difference? 29 minus 15z.
We can take 3 maybe.
3, yeah. But even 1. Even 1 is enough.
Yes.
So let z be 1. So then our equation is equivalent to what? So we have the following. 6x plus 10, y equals 29 minus 15, that is 14. Does this one has a solution?
Yes.
Exactly, because the greatest common divisor of these two numbers, which is 2, divides 14. But can we obtain a solution? Of course, we can solve it formally, but can we guess a solution?
Maybe x equal 4 and y equals minus 1.
4 and minus 4. So 60
minus 1.
minus 40, no.
Minus 1. Y equals
24 minus 10. Yeah, why not? We see that 6 multiplied by 4 minus 10 multiplied by 1 is 24 minus 10, that is 14. Okay, so we have obtained a solution. Which one? 4, this is the value for x, minus 1 for y, and 1 for z is a solution to our equation. So there is a solution. There is a solution, and it is not that hard to find all possible solutions. To find all possible solutions, and they will obtain, they will comprise a two-dimensional subspace, a plane in three-dimensional space. Of course, only integer points count here. Is it clear? But look, in our solution, we have a negative number. But is it possible to obtain a solution with all integers being positive, or at least non-negative? Does our equation the same one? Does it have a solution? In naturals, that is where x, y, and z are all greater or equal than 0.
No.
What do you think?
No.
Why?
Like, if we take...
Assume that x0, y0, z0 is such a solution. So what do we have? 6x0 plus 10y0 plus 15z0 equals 29, and all these numbers are non-negative. What's the problem here? Think of divisibility relations between these numbers. May all of them be 0?
Obviously no.
May anyone be 0?
Not really.
If x naught is 0, then what do we have? 10y0 plus 15z0 being equal to 29, right?
Yeah, but 29, greatest common divisor of 10 and 15.
Yes, these both numbers are divisible by 5. Hence, 5 must divide 29, which is clearly not the case. What about y?
Then greatest common divisor is 3,
Mm-hmm.
and it's not contradiction also.
3 must divide 29, which is not the case, so it is not possible. And what about z? If z0 was 0, we know that it is not possible, it must be odd. But nevertheless, let us repeat. So we have 6x0 plus 10y0 being equal to 29. So what does it mean? 2 divides 29, which is not the case. So x0, y0, and z0 are all greater than 0. That is, all these three numbers are greater or equal than 1. Do you agree?
Yeah.
And if as they are greater or equal than 1, what about the left-hand side of our equation? What about the left-hand side of our equation?
It's greater than 31. Equal greater. Greater.
Exactly. It is greater or equal than 6 plus 10 plus 15. But this number is 31, which is clearly greater than 29. So this triple of numbers cannot make a solution. Is it clear?
Yeah.
There is no solution which consists of non-negative integers, of naturals. Let us solve a congruence. A very simple linear congruence. Do you know how one can solve it? Do you know this theory? You'd better revisit the lecture notes. What is the solution to a congruence by definition, ladies and gentlemen? What is called the solution to such a congruence?
A number that
satisfies this congruence and
lies in a range of 0 and 9.
But can we find one? It is not hard to find this number directly by guessing, by brute force, by trying all our 9 possibilities for x. But of course, there is a better way. First of all, let us recall some theory. When such a congruence, in principle, has a solution, do you remember? Do you remember this theory?
When A and M are coprime?
Not necessarily so. If they are, it has a solution, but there are other cases.
When their greatest common divisor divides C?
When the greatest common divisor, let's call it D, AM divides C. Yes, that's it. Why is it so? It is not hard to understand. Because this congruence says that m divides this difference. Or equivalently, for some y, ax minus c equals my. Or equivalently, for some y, ax minus my equals c. So, but there is a solution. So there exists x. That means that there exists such x and y if and only if this equation has a solution. But we know that it has a solution if and only if the greatest common divisor of its coefficients, the sign means nothing here, you know, because the greatest common divisor does not, so it doesn't matter whether you have negatives or positives, what you feed to the greatest common divisor. Is this idea clear?
Yeah.
But what if indeed D divides C? Assume that D indeed divides C. Assume that our D divides C. Then, which solutions do we have? How many of them?
Greatest common divisor.
But what was our notation for this number?
X0 or something like this.
Really? Wasn't it D?
D probably.
The greatest common divisor.
Oh yeah, D solutions. Yeah.
Has exactly D solutions. Which ones?
So just x0 the solution. Then
Some x0. We shall explain later what it is. X0 plus.
x0 plus d, x0 plus 2d, all the way to the
No, not plus D, but plus M prime.
Oh. Yeah.
And now let us explain this notation. So x0 and then with a period of M prime, we have D minus 1 more solutions. Overall, we have D solutions. Is it clear?
Yeah.
Where? What is M prime?
M divided by greatest common divisor by D.
Exactly. Also, we need A prime, which is A over D. It is an integer. And C prime, which is C over D. And what is X0?
Solution to the
And such a solution is unique. Is a unique solution to what? To another equation, a congruence.
Yeah, a prime x congruent to C modulo M prime. S prime.
Yeah. Look. This congruence results from this one. If I divide all these numbers, A, C, and M, by D. Do you agree?
Yeah.
And now let us apply this theory to our particular congruence. First of all, here we have A. What is A? What is A here?
An integer.
It is 12, isn't it?
Oh.
What is M here?
9.
9.
What is C here?
Minus 15.
Minus 15. Okay, what is D here? The greatest common divisor of A and M.
3.
3.
The greatest common divisor of 12 and 9. It is 3. Aha. So what is M prime? 9 over 3, that is
3, yeah.
A prime,
4,
C prime.
-5.
What was C? C was minus 15. So minus 15 over 3. It is divisible by 3, so the result is -5. So we have another congruence, this one, for which we know one and only one solution exists. -5 modulus 3. First of all, we can simplify it. What is -5 modulus 3? What is the remainder of -5 modulus 3?
1.
Exactly. But can we solve such a congruence? Of course, formally, we need Euclidean algorithm, but here there are just 3 possible remainders, so it is obvious how can we guess it. What is the only solution to this congruence?
1.
Yeah, 1! 4 multiplied by 1 is congruent to 1 modulus 3. Do you agree?
Yeah.
So for the original congruence, we have what?
X not equal to 1. Which is a solution also.
The same plus m prime. 1
yeah.
plus what?
3.
The same plus twice m prime. We should have we should have 3 solutions. 1, 4,
3.
and 7. Is it clear?
Yes.
All these numbers, it is immediate, it is obvious, are solutions to this congruence, and they are pairwise distinct. They are pairwise distinct. They belong to our range from 0 to 9. Let us check that they are indeed solutions. For 1, it is quite clear. 12 multiplied by 1 is what? It is 3, which is the same as -15 modulo 9. What about 4? 12 multiplied by 4 modulo 9, what is it? 12 modulo 9 is what?
3.
So it is 3. So we have what?
12 again, so 3.
12 again, yeah. Which is the same as -15 modulo 9. And what about 7? It is 3. And 7 is -2, yeah?
Yeah.
-6. But 15 is congruent to 6 modulo 9. So it is -15 modulo 9. And all the other remainders, all the other numbers in our range are not solutions. Is it clear?
Yes.
We can find all the solutions and only solutions. The next one. Let us solve a system of congruences of the simplest kind, of the simplest form. Assume that they are of the following form. X is congruent to 12 modulo 15. X is congruent to 8 modulo 17. And X is congruent to 3 modulo 4. How can we solve it? Which theorem says anything about solving such a congruence, such a system of simultaneous congruences?
Chinese remainder theorem.
So what? What does that theorem tell us?
If such system has a solution, if all the modulus are coprime, pairwise coprime.
Yes, and they are pairwise coprime. Clearly, the greatest common divisor of 15 and 17 is 1, because 17 is a prime number. The greatest common divisor of these two numbers is 1, and the greatest common divisor of 15 and 8 is also 1. So, by the Chinese remainder theorem, according to the Chinese remainder theorem, this system has a unique solution. A unique solution where? Between 0 and what?
The
Product.
The least common multiple or product, minus 1, of course. So we want to include it into this range. Is it clear?
Yeah.
How can we solve it practically? What do we know?
Like we can turn it into
Two equations, into two congruences. Yes, but how can we do so?
so we can like
First of all, we can take any two of these congruences. Say the two first congruences. Let us focus on this system. How can we solve it? We know the formula. What was the main idea?
Like cross.
Yeah, but crossing some numbers require knowing what? Two coefficients. What do we need? As 15 and 17 are co-prime, which coefficients we may obtain? Which ones may we obtain?
like the them.
Such u and v that
Like 15 multiplied by u plus 17 multiplied by v is equal to 1.
yes, the greatest common divisor. By the way, can you see the whiteboard?
Yes.
Yeah.
Okay, I'm writing just that. So let us find these numbers. How can we do so? Formally by
Euclidean algorithm.
the extended Euclidean algorithm. But maybe here it is not hard to guess it. Let us try guessing, but some improved guessing. What is the idea of improved guessing? Let us take some values of u and v, which are easy to compute, for which the sum is easy to compute. And then let us somehow obtain 1. What if, say, I take 1 and minus 1? What the result will be?
-2.
-2. So I have -2, but I need 1. What else? What if, say, I take 2 here and minus and -1 here?
13.
13. But can we obtain 1? It is, after all, it is odd. and this one is even. Can we obtain 1 by adding together 13s and 2s?
Sure.
What is 1? 1 is 13 plus
Minus 6
6
minus 2.
copies of minus 2. Do you agree?
Yes.
That means that 1 equals what? It equals 6 copies of this one plus 1 copy of this one. Is it clear?
Yeah.
So what is it? Here I have 15 multiplied by 6 plus 17 multiplied by minus 6 plus 15 multiplied by 2 plus 17 multiplied by minus 1. So considering similar terms, I have 15 multiplied by 8 plus 17 multiplied by minus 7. Can you check it directly? Is it true? What is 15 multiplied by 8?
120.
Yeah. What is 17 multiplied by 7?
Minus
70 plus 49. So it is 119. Do you agree?
Yes.
So it is 1. So far, we have successfully guessed our U and V. What is the next step? The next step is this crossing procedure. So we have as follows. 1 equals 15 multiplied by 8 plus 17 multiplied by minus 7. This was 1. But now I want to define some number x1. I shall take these terms and modify them a little. I shall multiply this one, where we have 15, by 8. Is it clear?
Yes.
Yeah.
And here I have 17. And I will multiply it by this remainder, that is by 12. Is it clear?
Yes.
It is not hard to see that this number is indeed not a solution, of course, but this number satisfies the congruence. Why is it so? Easy. What is 17 multiplied by, let us check, for example, that it satisfies the first congruence. What is it? Here we have 15 multiplied by 8 squared. And what is 17 by minus 7? You know it is 1 minus 15. It is 1 minus 15 multiplied by 8. Do you agree?
Yeah.
Everything must be multiplied by 12. Okay, but what is x1 minus 12? It is just 15 multiplied by 8 squared minus this thing, minus 15 multiplied by 8 multiplied by 12. This is divisible by 15. Is it clear?
Yes.
Yeah.
So that means that this number is divisible by 15. Likewise, I can prove that x minus 8, likewise, x minus 8 is divisible by 17. So it is almost a solution, but still it is not a solution. Because it is, why isn't it a solution?
It just satisfies two congruences.
Yes, it is out of range. But let us put it in range. Let us consider x2 and take the remainder of x1 modulo 15 multiplied by 17. It is not very hard to do so. Look, what do we have here? We have so we need to consider the remainder. X1 is 15 multiplied by this number plus 17 multiplied by minus 7 multiplied by 12. Do you agree?
Yep.
The main idea here is to spot copies of 15 multiplied by 17. Let us do so. Let's do it without a computer. Of course, using a computer, it is very easy to find the remainder. Let us do without a computer. Here we have 8 squared. What is 8 squared?
64.
It is 64. But what is 64 modulo 17? It is 34 plus 30. So here we have 3 copies of 17. What is 3 copies of 17?
51.
51. So here we have 17 multiplied by 3 plus
13.
Look here. What is 7 times 12?
80 minus 84.
It is 84. 7 times 12. But 84 is 9 minus 6. Do you agree?
Yeah.
But what is 90 minus 6? It is 15 multiplied by what?
6.
Minus 6. Do you agree?
Yes.
Yeah.
So what do we have here? We have 15 multiplied by 17 by 3 plus 15 multiplied by 13 minus 17 multiplied by 15 by 6 minus plus 17 multiplied by 6. Do you agree?
Yes.
But these terms are 0 modulo 15 multiplied by 17. So we have 15 multiplied by 13 plus 17 multiplied by 6 modulo 15 multiplied by 17. What can we do with this? It is 15 multiplied by 17 minus 15 multiplied by what? By 4. Do you agree?
Yeah.
This is still 0. So we have 17 by 6 minus 15 by 4. Can we compute it directly?
We can.
What is it? It is 42. Do you agree?
Yeah.
But was it true? 42 modulo 15 is what? Is it 12 modulo 15?
Yeah.
But is it 8 modulo 17?
This.
42 minus 8 is 34. It is divisible by 17. Do you agree?
Yes.
Yeah.
So we see that as x2, our solution is just 34. But we know that this whole system of these two, this entire system of these two congruences is congruent to one congruence. Which one? X is congruent to what?
42.
Which modular?
15 multiplied by 17.
Exactly. So that means that x is congruent to 42, this modular, and here I have x congruent to 3 modular 8. How can I solve this one? The same idea with crosses, but still I need to find two coefficients, u and v, such that 15 multiplied by 17 multiplied by u plus 8 multiplied by v equals 1. Okay, how is it possible? Can I guess it? Can you guess it? Is it that hard? After all, what is 15 multiplied by 17? It is 15 squared. It is 15 squared plus what?
30.
But 15 squared is what? Do you agree?
Yeah.
Ha! But now it is almost obvious. What is it? It is 200, a power of 2 to the power 8 minus 1. And here I have power 3.
Yeah, so 1 and minus 1 and 32.
Yes. I can easily apply Euclidean algorithm here. Because here I have this exponent. So it is, what is the partial quotient here? What is it? It's 16, yeah? You can easily do it. So what do we have? This part is 2 to the power 8 multiplied by u plus 2 to the power 3 multiplied by v plus u. How can I make it being equal to 1? What should I take for u? What should I take for v?
Minus 1 and 32.
Minus 1, yeah, really? Or 1?
No, minus 1. Minus 1 for you. Oh. Or maybe not. No. It holds for the first system. No. Minus 1.
And here we need minus. So what the result will be? So 2 to the power 8 minus 1 multiplied by 1 plus 2 to the power 3 multiplied by minus 2 to the power 5. What is it?
Minus 2.
No. It is -1.
-1, yeah.
Mm-hmm. So apparently you were right. Let us take -1 here and plus here. So then we have 2 to the power 8 multiplied by -1 plus 2 to the power 8 minus -1. Yeah, the problem was in this sign. It was not correct. Here we have 2 to the power 8 -1. Yeah? Now everything is okay. Is it clear?
Yes.
Yeah, yeah.
We have found u and v, and how can we solve it? How can we solve it? Let us do our crossing. What is the solution may be? So we take 15 multiplied by 17, that is this number, multiplied by -1, plus we take 8 multiplied by 32, 2 to the power 5, and then we should do some crossing. Multiply this one by what?
42. Oh, by 3.
By 3, and this one
By 8. Oh, by 42. Oh.
by 42. Is it clear?
Yeah.
And now we are interested in the remainder. The solution is just the remainder of this number modulo, so it is this number multiplied by 8. And this number is quite easy to find. It is 2 to the power 8 minus 1 multiplied by 2 to the power 3. What is it? 2 to the power 11 minus 1. What is it? What is 2 to the power 11?
Y -1.
What?
Y -1.
Yes, -8. Thank you. So what is 2 to the power 11?
2048.
And here we have just 8. So it is 2040. Do you agree?
Yeah.
And we need the remainder. So what is it? 15. This number minus multiplied by -3 plus 2 to which power? 2 to the power 8 multiplied by 32. We can easily find out the result. So here we have this number plus this one. Do you agree?
Yeah.
So it is 255 multiplied by what? 42 minus 3, 39. Am I right?
Yes.
But what is it? This number multiplied by 8 multiplied by 4 plus 7. That is our remainder, our modulus plus this number plus 32. It is 0. So we have this one plus 42. Can we compute it? Directly. It is easier. So what is the result? Is it? Am I right, ladies and gentlemen?
I think it's
Yes.
160, no?
Where?
No, it's 700. It's okay.
Oh, I thought it was 3 multiplied. Sorry, yeah, that's right. Okay.
What is the final result?
Uh, 100.
1827. Or isn't it?
Yes, yes, it is.
This is a solution and you can check it directly. There are no other solutions according to the Chinese remainder theorem. Is it clear?
Yeah.
So to
We
the
had-
whole
Uh-huh.
congruence, to the whole congruence star, we have the unique solution, which is 1827.
Yes, exactly. This is equivalent to the following. X is congruent to this number modular 15 multiplied by 17 multiplied by 8. So this is the solution. Is it clear?
Yes.
But how can one solve other congruences of other forms where we have some arbitrary polynomials? Assume that we are interested in the following polynomial. Let us see whether we are able to solve it. Plus 9 is congruent to 0. This polynomial is congruent to 0 modulus 35. Let us solve it. How can one proceed? The most obvious option is to try all 35 remainders modular 35. Is it clear? You can brute force it. You can search for all solutions directly, taking all the numbers, trying all the numbers, 0, 1, 2, and so on, up to 34. Is this idea clear?
Yes.
But there is a better way. First of all, what is 35?
36 minus 1, I don't know.
And what of it? It is 5 multiplied by 7, where 5 and 7 are co-prime. Do you agree?
Yeah.
My congruence means that 35 divides P of x. Its remainder is 0, so it is divisible by 35. But when something is divisible by 35,
But it's
according to-
divisible by 5 and by 7.
exactly. So that means that my system is congruent. My original congruence is equivalent to the following system. P of x is congruent to 0 modulo 5, and P of x is congruent to 0 modulo 7. Is this idea clear?
Yes.
And now let us try solving everyone. Here we have much less remainders to check. Okay, modulo 5. P of 0 modulo 5. Let us reproduce, so this is our polynomial. What is P of 0?
9.
9.
And modulo 5?
4.
4. Is it 0? No. P of 1. What is P of 1? 1 plus 2 plus 8 plus 9. Do you agree?
Yes.
But what is it? It is 20. And modulo 5? It is 0. So 1 is a solution to the first congruence. Do you agree?
Yes.
What about 2? Look, here we have some powers of 2. 2 to the power 4 plus 2 to the power 4 plus 2 to the power 4 plus 9. What is it? 16 multiplied by what? Ladies and gentlemen, please be present. What is it?
We are present.
16 multiplied by 3. But what is 16 modulo 5? It is 1. And 9 is 4. So that's it. It is what? 7.
7 or 2.
Or 2. It is not 0. So 2 is not a solution. And what about 3? I can simplify things a little. 3 is what modulo 5?
-2.
Exactly. It is -2. So I will obtain the same here, but with different signs at our odd degree terms, odd degree monomials. So I have 2 to the power 4 minus twice 2 to the power 3 minus 8 multiplied by 2 plus 9. So what is it?
It is
Minus 16 plus 9.
-7.
which is
Minus 7. Really? Yeah, that's it. It is not 0. Not a solution. And what about P of 4? What is it?
-1. P of -1.
The same here, save the signs. 1 minus 2 minus 8 plus 9. It is what? 0. So we have obtained so far 2 solutions. Do you agree?
Yeah.
Yeah.
There are exactly 2 solutions to the first one. But what about the second one? What should we do?
Take the solutions and check if
Take what? 1 and 4?
Yeah.
No way. See, here we have 1 and 4 modulo 5. These numbers are independent of their remainders modulo 7. According to the Chinese remainder theorem, if your remainder modulo 5 is fixed, your remainder modulo 7 can be anything. Our solution is not 1 and 4. Our solutions are 1 and 4 modulo 5. But modulo 7, I have other meanings of these numbers. Is this idea clear?
Yeah.
Practically, that means that I have to recheck every remainder, but modulo 7. Look, what the result may be. So let us rewrite our polynomial. Okay. P of 0, it is 9, and modulus 7, it is what? 2, not a solution. P of 1. P of 1 was this number. And modulus 7, what is it? It is 20, or modulus 7 minus 1, not 0. P of 2, what was it? 16 multiplied by 3 plus 9. But modulus 7, what is 16 modulus 7?
2.
Here we had not just congruences modulo 5, but equations. So these are absolute. These are true for every modulo. These are equations, in fact. So, but then I used the fact that our modulus was 5. But now let us do the same for 7. 2 multiplied by 3 plus 2. What is it?
It is 8.
8 or 1 modulus 7. Not a solution. Do you agree?
Yes.
3. What about 3? It is not possible to do this trick now. So we have 3 to the power 4 plus twice 3 to the power 3 plus 8 multiplied by 3 plus 9. But anyway, we can simplify it a little. What is 3 to the power 4? What is 3 to the power 3? Modulus 7.
27.
Really?
Oh, modulus 7.
It is 6. Or just minus 1 modulus 7. Do you agree?
Yeah.
So, what is it? Here we have 3 multiplied by minus 1, minus 2, multiplied, plus 2 multiplied by minus 1, minus 2, plus 8 multiplied by 3, 8 is 1, plus 3, and here we have 9, that is 2. Ha! What is it?
0.
0. So it is a solution. 4. But what is 4 modulo 7?
Minus 3.
Exactly. So we have the same as here. Save the signs. Minus twice 27 minus 8 multiplied by 3 plus 9. So it is minus 3, but now change the sign for these middle terms. Plus 2 minus 3 plus 2, what is it? Minus 6 plus 4, what is it?
Minus 2, so not 0.
Minus 2, not a solution. 2 more remainders. 5.
Minus
5 is the same as minus 2. So we have the same as here. Look. Here we have 16 plus 16 plus 16. But now we shall have something else. 16 minus 16 minus 16 plus 9. Do you agree?
Yes.
Yeah.
What is it? Minus 16 plus 9, which is
Minus 7.
Minus 7.
or 0 modulo 7?
Oh.
Do you agree?
Yes.
So it is a solution. The last one. P of 6 or P of minus 1. What is it? The same as here, except the signs. 1 minus 2 minus 8 plus 9. It is 10 minus
10.
10 minus 10. So it is 0. But apparently we have some problem, some error somewhere. Maybe here. Aha. Yeah, that's not true. It's not true. So, OY minus 3 is 84 divisible by 3. It is. So here we have minus 2. It cannot be a solution. There should be, or maybe. Do you see any error here, any mistake on our part? Or probably everything is true? Can anybody check?
I think we did write everything.
Okay. Assume that we are right. So far, we have solved every of these congruences. But what does it mean that we solved it? Look, that is the most interesting part. P of x is congruent to 0 modulo 5. We solved it, and we established that this is possible in exactly two cases. When x is 1 modulo 5 or x is 4 modulo 5. Do you agree?
Yes.
Yeah.
Likewise, this congruence that P of x is congruent to 0 modulo 7 is equivalent to the following disjunction. X is either 3 modulo 7 or x is 5 modulo 7 or x is 6 modulo 7. So our original problem, let's do it. We need about 10 times, about 10 minutes. Our original problem is equivalent to the following system, that is conjunction of disjunctions. We see that our original problem is equivalent to the following. X is either 1 or 4 modulo 5, or x is 3 or 5 or 6 modulo 7. Do you agree?
Yeah.
But here we have something like that. It is a disjunction, while this is a conjunction. Let us use our knowledge of logic. We have something like that. A or B and C or D or E. How can we apply distributivity to it? We can open the brackets. How? A and C or
A and D, A and E, and so on.
or A and E or
B, C, BD, BE.
So how many of them?
6.
6. 3 multiplied by 2. And this is a disjunction. So that means that this system is equivalent logically to a disjunction of the following systems. Look, this is A. X is congruent to 1 modulo 5 and 3 modulo 7. X is 1 modulo 5. X is 5 modulo 7. X is 1 modulo 5. X is 6 modulo 7. And all the same, but for the other remainder, modulo 5. Fourth, it is minus 1. Yeah. And we know the formulas. It is easy to solve every such a system. What should we do? Do you remember our crossing method?
Yeah.
But at the heart of this method lies finding u and v, for which 5u equals 7v. And 5u plus 7v equals 1. What can we take? Let us guess them. It is easy.
Minus 7, v minus, okay.
3 and minus 2. 15 minus 14 equals 1. Is it clear?
Yeah.
So how can we solve it? It is very easy. Write down this this one. 5 multiplied by 3 plus minus 7 multiplied by 2. And now we shall multiply them by something. This term with 5, we shall multiply by what? By this number, which is?
3.
And this term by what?
1.
What is it? Compute the result, please. 45 minus
14, which is 31.
1.
31. Does it work? Is 41 1 modulo 5?
Yes.
Is it 3 modulo 7? 28 is divisible by 7.
Yep.
What do we have here? Still the same numbers, but multiplied by what? This with 5 is multiplied by 5. This with 7 will be multiplied still by 1. And likewise here, 6 multiplied by 5 by 3 minus 7 multiplied by 2 by 1. Let us compute. So here we have what? 75 minus 14.
$61.
61 and modulo 35 minus 9, or equivalently 26.
Yes.
It is 26 modulo 35. Is 26 congruent to 1 modulo 5?
Yes.
Is it congruent to 5 modulo 7?
Yes.
What else here? 30 by 3 minus 14. What is it? 90 minus 14.
76.
Modulo 35.
6.
Just 6. and 6 satisfies this system. Here, the same numbers, 5 multiplied by 3 minus 7 multiplied by 2, but now this one with 5 will be multiplied by 3, and this one now by 4 or by minus 1, which is the same modulo 5. But anyway, let us compute. Okay, give me the result. 45 minus 35 minus what? Minus 56, yeah?
Yes.
What is it?
Minus 9. No, 11. Minus 11.
Minus 11 modulo 35. 24.
24.
Is 24 4 modulo 5?
Yeah.
Is it 3 modulo 7?
Yeah.
So next, we shall have 5 multiplied by 5 by 3 minus 7 multiplied by 2 by 4. What is it? 75 minus 56. $75 minus 56.
19.
It is 19. Does 19 satisfy this one?
Yes.
It is 4 modulo 5 and 5 modulo 7. Exactly. And the last one, 90 minus 56.
34.
34. And 34 is 4 modulo 5 and 6 modulo 7. Do you agree?
Yes.
So, what are the solutions? The solutions to our original congruence are exactly 31, 26, 31, 26, 6, 24, 19, 34. We have 6 distinct solutions. Is it clear?
Yes.
So our polynomial of degree 4 has how many roots?
6.
6 roots. How is it possible? We know that a polynomial may have no more roots than its degree. But this is true when we are working in a field. In particular, when we take remainders modulo a prime. But if we take remainders modulo a composite number, everything may change. We may have more roots than the root of the degree of this polynomial. Is this idea clear?
Yeah.
Yes.
Okay, do you have any questions?
Not really.
I have a question, a control question to you. After all, we are going to have an exam and so on. How could you solve something like that? Twice x is congruent to 22 modulo 34, and say x is congruent to minus 6 modulo 19. What should you do?
Unite them in.
What do you mean by unite them? First of all, you know, our Chinese remainder theorem is not directly applicable here, because our theorem requires all the congruences to be in the simplest form. X is congruent to something.
Oh, okay. So 2x congruent to
2 is the same as x congruent to 11.
Exactly. But we should keep modulo 34 because we must, you know, the greatest common divisor of 34 and 19 is 1. But so the least common multiple is what?
54 by 9.
It is the product. So we are obliged to find solutions this modular. Is it clear?
Yeah.
We cannot replace it by a congruence modulo 11. Why? Because we are interested, not modulo 11, excuse me, modulo 17. Because we are interested in solutions this modulo. But what should we do? Nevertheless, we should solve it modulo 34.
But
Exactly.
can we divide both parts by 2?
We can,
Okay.
but we can take an account of solutions. There will be 2 solutions.
Oh, okay.
Do you know this series? So it is like 11 modulo 17. They are equivalent. Is it clear?
Yeah, and because they
But
are
we
greatest
have
common.
more solutions. We have more solutions. Modulo 34. Modulo 34, we have 2 solutions. 11 and what? Plus
11.
m prime.
11 plus 17, yeah.
So modulo 34, we have these solutions. 11 plus 28. Do you agree?
Yeah.
Hence, we can do the following trick. We shall replace it by this one. X is congruent to 11 modulo 34. Effectively, I have solved it. Is it clear?
Yeah.
Effectively, I have solved it. 28 modulo 34. And now then, knowing that A and B or C is logically equivalent, please do not say congruent, the same symbol, but another meaning, is logically equivalent to A and B or A and C. Do you agree?
Yes.
Yeah.
So this one is logically equivalent to this one. X is congruent to 11 modulo 34. X is congruent to, to minus 6. To I have also got tight a little, but anyway, we need patience. And even more patience. Please be patient. So this eraser has run amok. It is erasing whatever it wants. Please, just wait a little. Let this program to come back to its feelings. Yeah. Or how are they saying? I have forgot the right idiom. Oh. Can you see the whiteboard?
Yes.
Yeah.
Still can, but it should disappear. One moment. Excuse me. Today is what? What is the date today?
3rd of
It doesn't matter, but what is
3rd
the
of
date?
December.
Uh-huh. Have you had such an exercise in your high school course? What the date today? What is the day? Yeah, the winter months are December, January, February. Do you remember this stuff?
Yes.
Have you had such an exercise in your high school time?
Probably.
Oh,
What day is today? What?
yeah, something like that. What are the winter months, the spring months, the summer months? So here we have 28, still 11 and 28, minus 6 modulo 19, and the whole stuff is logically equivalent.
We don't see anything.
Yeah, sorry, are you writing anything?
I am.
We just see
but
like the previous
okay,
word still.
okay. Wait, just wait a little, wait a little. Let me just finish all these things. Not all of you have enough patience, as I see. Can you see the whiteboard now?
Yeah.
Yes.
Okay. Our final strike. Final strike. Minus 6 modulo 19. So our congruence, our system of simultaneous congruences is equivalent to these two, and each of those it can be easily solved using the Chinese remainder theorem, because the moduli therein 34 and 19 are co-prime. Is it clear?
Yes.
Yeah.
So you will obtain two solutions to the original system. And here, in the case of that polynomial, we had obtained 6 solutions. Quite surprisingly, but nevertheless. So this is a method, this is a general method. So to solve a system, solve every solution, replace it with such a disjunction, and then obtain a disjunction of systems, of conjunctions, each of which is solvable using by the Chinese remainder theorem. Thank you. Any questions?